You know that feeling, right? You ask an AI assistant a question, and it gives you an answer that sounds so incredibly polished and convincing, but it's just completely, totally wrong. It's a massive problem. So today, we're going to dive into a really clever engineered solution that's designed to tame these confidently wrong AIs and actually make them trustworthy.
In this question, it's not just some quirky little bug. It is a fundamental challenge in AI today. See, when an AI feeds you bad information, but it's dressed up in perfect grammar and this super confident tone, it's more than just annoying. It can lead to some really serious problems out in the real world.
The official term for this behavior is hallucination. It's basically when the AI just dreams up an answer. And from a business perspective, oh man, this is an absolute nightmare. A hallucination can wreck customer satisfaction, cause huge operational mistakes, or even put you in a tough spot with compliance. The real issue isn't just that the AI is wrong, it's that it has no idea that it's wrong. Okay, so what's the fix? Well, the goal isn't just to make the AI smarter. It's about making it more responsible. We want to get away from an AI that's always forced to take a wild guess and move toward one that has enough self-awareness to know when it's on solid ground and when it ought to just, keep quiet. A really great way to think about this is to picture the perfect employee, right? They don't just invent answers to look good. They give you solid, factual information when they have it, and when they don't, they say, let me double check that and get back to you. That's the exact behavior we want to engineer into our AI systems.
And this all really boils down to one key idea: accepting a trade-off. To be super reliable, the AI might have to just not answer some questions. And you know what? That's a good thing. We would much rather get an honest, "I'm not sure," than a completely fabricated answer delivered with a straight face. This whole new approach is all about prioritizing safety over just having a response no matter what.
All right, so how do we actually pull this off? This brings us to the core idea here, the big technical innovation. Instead of forcing the AI to give one single high-stakes answer, this new approach asks it to generate a small group of possible answers. It's a pretty simple idea, but it's an incredibly powerful shift in thinking. So here's the difference, side by side. The standard way, the baseline approach, it's like a single shot in the dark. The AI gives you one answer, and you just have to cross your fingers and hope it's right. The risk is totally uncontrolled. But this new conformal approach, it's different. It generates a set of candidates, which gives it the power to control the risk and only give you an answer when it's safe to do so. And this really gets to this simple statistical advantage that's at play. I mean, think about it. If you ask for the single best movie of the year, that's a tough, debatable question. But if you ask for a short list of 5 really great movies, it's way easier to create a list where you know for sure at least one of them is a top contender, right? The exact same logic applies here. So let's talk about the roadmap. This isn't just some abstract theory. It's a practical, step-by-step process. We're going to pop the hood and walk through the flowchart of this system to really see how it makes these super reliable decisions. The whole thing really comes down to 3 core actions. First, it samples, generating a bunch of different potential answers from the model. Then, it filters out all the junk, the bad answers, the duplicates. And finally, and this part is absolutely key, it has a rule that tells it when to stop, locking in a set of answers that it's truly confident about. Let's look a little closer at that filtering step, because it's pretty smart. The quality filter is kind of like a bouncer at a club. It just throws out any answers that are poorly written or that the model itself has already flagged as being low confidence. Then the diversity filter steps in to make sure you don't just get 5 slightly different versions of the same bad idea. The end goal is to get a clean, varied set of really strong contenders. Now, what really makes this system so efficient is this stopping rule. See, it doesn't just blindly generate, say, 10 answers every single time. It keeps sampling and checking until the confidence in the entire group of answers hits a certain target. The second it's confident that the set contains a winner, it stops. That saves a ton of time and computing cost. But wait, how does this system even know what confident enough means? That question brings us to the secret sauce of this whole thing, calibration. This is the step that turns a clever heuristic into a mathematically sound method for building real, measurable trust. The reason it's called a conformal method is because its rules, things like how strict the filters should be or when to stop sampling, they aren't just arbitrary guesses somebody made up, they are learned. The system is trained on a whole separate dataset of questions and their known correct answers, and it tunes its own rules to hit a very specific reliability target, like, I need to be right 99% of the time. The tool it uses for this teaching process is called an admission function. Now that sounds fancy, but it's really just a simple binary check. For this question, is this answer acceptable or not? Yes or no? By running thousands of these checks during that calibration phase, the system learns what a good answer looks like and, more importantly, how to build a set of answers that's guaranteed to have one inside. Okay, this all sounds amazing, but like any good engineering solution, there are always trade-offs. You don't get this level of reliability for free. You have to strike a balance between being right, being helpful, and being efficient.
And what that creates is this three-way tug-of-war. So if you dial up the reliability, you demand a lower failure rate, you will almost certainly decrease the coverage. Because the model's going to say, I'm not sure, a lot more often. At the same time, you're going to increase the cost, because it needs to generate more samples to find a set it feels good about. The beauty of this system, though, is that it lets you pick your own balance point for your specific needs.
Maybe one of the best things about this whole approach is just how practical it is. You don't have to build a new AI from the ground up. This works as a reliability layer that you can just put on top of many existing models. It's absolutely perfect for those high-stakes situations in finance or healthcare or customer support, anywhere the cost of one single wrong answer is just incredibly high. But let's be real, it's not a silver bullet. We got to be honest about the limitations here. For instance, if the kinds of questions our users are asking suddenly change, well, that original calibration might get stale and not work as well. The system is also only as reliable as the quality check you use to define what a good answer even is. And of course, making more calls to the AI costs more money, and it takes a little more time.
So let's wrap all this up and get to the big picture takeaway. This is really about more than just a clever algorithm. It's about a whole new philosophy for how we design AI. It's really about engineering for responsibility.
Ultimately, what this shows us is that we don't have to just live with AI hallucinations. By shifting our whole approach from demanding a single, risky guess to generating a calibrated shortlist of answers, we can actually build systems where reliability is a feature, something we can control, measure, and truly depend on. And that kind of leaves us with one last thought to chew on. As we get better and better at building these safer, more responsible systems, maybe the most impressive thing an AI will be able to do isn't giving us some brilliant, unexpected answer, but having the wisdom to know when to just say, I don't know. What do you think?